Gain a holistic view of equipment maintenance. Understand maintenance beyond routine tasks by considering system-wide impacts and long-term reliability. Explore key elements of asset management. Learn how asset acquisition, utilization, and disposal contribute to overall business efficiency. Understand the link between maintenance, reliability, and asset management. Discover how maintenance practices influence reliability and align with broader asset management strategies. See the big picture, connecting maintenance goals to business objectives. Recognize how effective maintenance supports productivity, profitability, and risk reduction. Develop and implement asset maintenance strategies. Learn structured approaches to designing and executing maintenance plans that maximize asset longevity. Analyze asset lifecycle costs, maintenance expenses, and total ownership costs. Understand direct and indirect costs to make informed financial decisions. Apply RCFA, FMEA, and RCM methodologies. Use structured failure analysis and risk-based approaches to improve asset reliability. Master maintenance planning and scheduling principles. Enhance work execution efficiency by optimizing resource allocation and minimizing downtime. Optimize spare parts management and inventory control. Implement techniques to reduce stockouts, overstocking, and unnecessary holding costs. Analyze asset lifecycle costs, maintenance expenses, and total ownership costs. Understand direct and indirect costs to make informed financial decisions. Monitor asset and reliability performance indicators. Use data-driven insights to track efficiency, prevent failures, and improve maintenance effectiveness. 1. Equipment reliability. Equipment reliability ensures that machines perform consistently without unexpected failures. It involves proactive maintenance, data-driven decision-making, and adherence to best practices. Reliable equipment reduces downtime, enhances productivity, and extends asset lifespan, ultimately supporting operational efficiency and business continuity. 2. Risk reduction. Reducing operational risks minimizes safety hazards, financial losses, and production disruptions. A structured approach, including predictive maintenance, proper training, and adherence to industry standards, helps identify and mitigate risks early. This leads to safer work environments and improved decision-making. 3. Defect elimination. Defect elimination focuses on identifying and correcting root causes of equipment issues before they escalate. Techniques such as root cause analysis, RCA, continuous improvement, and condition monitoring ensure equipment operates optimally, reducing the chances of recurring failures and inefficiencies. 4. Least operating cost. Efficient maintenance strategies, optimized resource utilization, and energy-efficient operations help achieve the lowest operating costs. By preventing breakdowns, extending asset life, and reducing waste, organizations can minimize expenses while maintaining high reliability and performance. 5. Maximum production. High equipment reliability, minimal risks, and proactive defect elimination collectively drive maximum production output. When machines operate smoothly with minimal interruptions, production targets are met efficiently, leading to higher profitability and market competitiveness. 6. Failure avoidance. Failure avoidance strategies, such as predictive maintenance, real-time monitoring, and process optimization, ensure continuous operations. Avoiding failures not only prevents costly downtime, but also enhances worker safety, reduces repair expenses, and improves overall asset dependability. Breakdown maintenance. This type of maintenance is performed when equipment unexpectedly stops functioning or when a fault is identified and reported by the production team. Preventive maintenance. Scheduled and predefined maintenance activities are conducted on equipment at fixed intervals based on calendar dates, usage levels, operating hours, or mileage. Predictive maintenance. The condition of equipment or specific performance indicators is continuously monitored at predetermined intervals. Maintenance tasks are planned and executed based on real-time parameter readings such as temperature variations, vibration analysis, and flow monitoring to optimize reliability and reduce failures. Condition-based maintenance. Maintenance activities are determined and executed based on observations gathered during scheduled inspections or unplanned assessments. These maintenance actions aim to address identified issues before they cause critical failures and are sometimes referred to as corrective actions. Risk-based inspections. Inspections are systematically scheduled based on the current condition of the equipment or an assessment of the potential risks involved in its operation. This approach prioritizes inspections based on criticality, ensuring resources are allocated efficiently to high-risk components. Opportunity maintenance. Maintenance tasks are strategically planned and scheduled based on the availability of equipment, taking advantage of production downtimes, product changeovers, or temporary unavailability of raw materials. Precision maintenance. Maintenance activities are carried out in strict adherence to technical standards governing equipment operation and reliability. This includes balancing and alignment standards, oil cleanliness regulations, fits and tolerances, torque tightening specifications, geometric tolerances, as well as storage and preservation guidelines to ensure optimal equipment performance. Proactive maintenance. A maintenance strategy focused on modifying, redesigning, or improving equipment functionality to enhance reliability and prevent future failures. This approach is driven by principles such as reliability-centered maintenance, RCM, and root cause analysis, RCA, ensuring long-term equipment effectiveness. Breakdown maintenance is carried out when equipment stopped or fault reported by production staff. Preventive maintenance. Predetermined maintenance activities are carried out on equipment based on calendar like monthly, yearly, or uses like hours, mileage. Condition-based maintenance. The maintenance tasks are determined and carried out based on observations of scheduled or ad hoc inspections. Predictive maintenance. The equipment condition or some function/performance parameter is monitored with predetermined frequency. Based on the value of parameter, maintenance tasks are determined and carried out. Proactive maintenance. All activities carried out to modify or redesign the equipment function are termed as proactive maintenance. Maintenance alignment with organizational objectives. Organization objective. Profit maximization. Market share growth. Customer satisfaction. Innovation and growth. Social responsibility. Asset management objective. Availability and reliability target. Life cycle cost optimizations. Quality and productivity targets. Catering future production demands. Strategic asset management plans. Plant maintenance strategy selection. Maintenance budgeting and people skilling. Maintenance plans executions. Asset performance monitoring. Continual improvement. Maintenance alignment with organizational objectives. Organization objective. Profit maximization. Market share growth. Customer satisfaction. Innovation and growth. Social responsibility. Asset management objective. Equipment reliability. Risk reduction. Defect elimination. Least operating cost. Maximum production. Asset management tasks. Breakdown maintenance, corrective maintenance. Preventive and predictive maintenance. Proactive maintenance. Spare parts management. Maintenance budgeting. Knowledge creation and management. Objective hierarchies. Approach A. Equipment reliability at highest priority and followed by risk reduction, defect elimination, failure avoidance, maximum production, least operating cost. Approach B. Maximum production, least operating cost, failure avoidance, risk reduction, defect elimination, equipment reliability. Big picture. Asset management frameworks. Frameworks are broad overview, outline, or skeleton of interlinked items which supports an approach to a specific objective and serves as a guide. Elements in maintenance frameworks. Organization objectives. Asset management objective. Asset management strategy and plans. Asset life cycles. Support system, skills, resources, information system. Performance review and continual improvement. Asset management frameworks. ISO Standard 55000, a global standard for asset management that ensures optimized performance, risk control, and cost efficiency. Global Forum on Maintenance and Asset Management. GRAFM Framework, a structured approach integrating governance, risk assessment. Uptime Framework, a methodology focused on proactive maintenance, reliability engineering. Total Productive Maintenance, TPM. Reliability-Centered Maintenance, RCM. a systematic process to determine the most effective maintenance strategy, ensuring equipment reliability while optimizing costs. ISO 55000, Asset Management Framework. An organization's plan and objectives drive its asset management objectives. These objectives align with business goals, ensuring assets contribute effectively to overall success. To achieve this, organizations develop strategic asset management plans, SAMP, high-level roadmaps that define how asset management aligns with corporate strategy. These plans guide the creation of asset management plans, AMP, which provide detailed actions for individual assets or asset groups. Implementation occurs at the asset portfolio level, where specific maintenance, operations, and investment decisions are made to optimize asset performance. Performance evaluation and continuous improvement ensure that asset management remains effective. Regular monitoring, audits, and feedback loops help refine strategies, improving reliability, cost efficiency, and sustainability. Supporting elements like leadership, risk management, competence development, information systems, and stakeholder engagement form the foundation of a strong asset management system. These ensure alignment, accountability, and continuous progress toward organizational goals. Global Forum on Maintenance and Asset Management. Business requirements shape an organization's objectives, which in turn define asset management goals. These objectives serve as the foundation for maintenance strategy management, ensuring alignment between asset performance and business success. Within maintenance strategy management, key components include asset register, asset criticality analysis, failure mode analysis, and maintenance planning. These elements help identify asset importance, failure risks, and necessary maintenance actions. The next level is maintenance management, which governs various maintenance approaches such as predictive maintenance, preventive maintenance, inspections, performance management, and corrective maintenance. These ensure a proactive and structured approach to asset upkeep. Maintenance execution takes place at the shop floor level, covering activities like maintenance requests, work planning, work coordination, work scheduling, work execution, and job completion reporting. This phase ensures that planned maintenance activities are carried out effectively. The ultimate deliverables include reliability, availability, compliance, and optimal lifecycle cost, key performance indicators of a successful maintenance and asset management system. Support elements, including skilled personnel, materials, tools, and technological resources, play a crucial role in enabling efficient maintenance execution and long-term asset sustainability. Uptime element in asset management framework. It can be structured into three primary levels: technical activities, leadership, and business processes. These elements work together to optimize asset uptime and ensure long-term operational success. Technical activities. This includes hands-on maintenance and operational strategies that directly impact uptime. Key aspects include preventive maintenance, PM scheduled maintenance tasks to avoid unexpected failures. Predictive maintenance, PDM condition monitoring and analytics-driven interventions. Reliability-centered maintenance, RCM-focused maintenance strategies based on failure modes. Work order management, ensuring maintenance tasks are tracked, scheduled, and executed properly. Failure analysis, root cause analysis, RCA, to eliminate recurring issues. Spare parts management, ensuring critical spare parts are available to minimize downtime. Leadership. Leadership plays a key role in defining asset management policies, strategies, and culture. Strategic vision, setting long-term goals for uptime improvement and operational efficiency. Reliability culture, encouraging proactive maintenance behavior across teams. Training and skill development, ensuring teams are equipped with knowledge on best maintenance practices. Investment in technology, implementing CMS, IoT, and AI-driven solutions for better asset monitoring. Cross-functional collaboration, aligning maintenance teams with operations, finance, and engineering for holistic decision-making. 1.3 Business processes. Uptime also depends on efficient business processes that integrate maintenance with overall asset management strategies. Asset performance monitoring, using KPIs like MTBF, mean time between failures, and MTTR, mean time to repair. Risk management, assessing asset-related risks and implementing mitigation strategies. Regulatory compliance, ensuring maintenance activities align with industry safety and compliance standards. Budgeting and cost control, allocating resources effectively to balance uptime and operational costs. Continuous improvement, using data insights to refine maintenance processes and enhance reliability. Total productive maintenance, TPM, overview. Total productive maintenance, TPM, is a comprehensive approach to equipment maintenance aimed at maximizing efficiency and reliability. Rooted in Gemba, the actual workplace, and 5S, sort, set in order, shine, standardize, sustain. TPM, or Total Productive Maintenance, is a comprehensive approach to equipment maintenance that aims to maximize the productivity and efficiency of manufacturing and production processes. TPM is built on several key pillars, each of which plays a crucial role in achieving its goals. These pillars are autonomous maintenance. Jishu Hosen. In this pillar, operators take responsibility for basic maintenance tasks on their equipment. This includes cleaning, inspection, lubrication, and small repairs. Planned maintenance. Kikodiai Hosen. This pillar focuses on proactive and planned maintenance activities. Maintenance tasks are scheduled in advance, and equipment is periodically inspected and maintained to prevent unplanned downtime. Focused improvement. Kaizen-focused improvement involves continuous improvement efforts to enhance equipment performance and overall process efficiency. This can involve identifying and eliminating sources of waste, reducing cycle times, and optimizing the production process. Quality maintenance. Hinshitsu Hosen. This pillar emphasizes the importance of preventing defects and maintaining consistent product quality. It involves addressing quality issues at their source. Education and training. Kyojo Kaizen TPM recognizes the importance of well-trained and skilled employees. This pillar focuses on providing training and development opportunities to equip employees with the knowledge and skills necessary to support TPM activities. Early equipment management. EM concentrates on designing, selecting, and installing equipment with a focus on maintainability and reliability. It ensures that equipment is capable of meeting production needs with minimal maintenance requirements. Safety, health, and environment. SHNE. This pillar emphasizes the importance of maintaining a safe and environmentally friendly workplace. Safety and health standards are integrated into the maintenance and production processes, ensuring the well-being of employees and the environment. Administration. Kibetsu Kaizen TPM's administrative pillar involves establishing the systems and procedures necessary to support and sustain TPM activities. This includes record-keeping, documentation, and performance measurement. TPM in office. TBM, Total Business Management TPM principles can also be extended beyond the shop floor to office and administrative processes. This pillar aims to improve the efficiency and effectiveness of administrative functions in an organization. By implementing these pillars, TPM strives to create a culture of continuous improvement, reduce equipment downtime, enhance product quality, and boost overall operational efficiency. Overall equipment effectiveness, OEE. It is a vital metric in manufacturing that evaluates how efficiently equipment operates. It is calculated using three key components. Availability ratio measures uptime by comparing actual running time to planned production time. It accounts for downtime due to breakdowns, setup delays, etc. Performance ratio assesses how fast the equipment runs compared to its design speed. Losses here include slow cycles, minor stoppages. Quality ratio evaluates the proportion of defect-free products to total output. Reliability-centered maintenance. Handbook on Maintenance Evaluation and Program Development, drafted by a maintenance steering group formed to oversee development of the initial program FO, are the new Boeing 747 airplane. TH's document, known as MSG-1. Use of the decision diagram technique led to further improvements, which were incorporated 2 years later in a second document, MSG-2, Airline Manufacturer Maintenance Program Planning Document. MSG-2 was used to develop the scheduled maintenance programs for the Lockheed 1011 and the Douglas DC-10 airplanes. In the 1970s, F. Stanley Nolan and Howard F. Heap, two engineers at United Airlines, played a significant role in advancing RCM. Their research focused on optimizing the maintenance strategy for commercial aircraft, and their work led to the development of the RCM methodology. The Nolan and Heap report provided the basis for MSG3, which was promulgated in 1980 and revised in 1988 and 1993. MSG3 remains to this day the process used to develop and refine maintenance program S for all major types of civil aircraft. It's important to note that MSG3 is a specific methodology used in the aviation sector. RCM, reliability-centered maintenance, is a broader concept applied across various industries, although they share similarities in their approach to maintenance. Introduction of John Mowbray's RCM2. 1990s. John Mowbray, a British engineer and author, introduced a widely recognized RCM methodology, known as RCM2, in his book, Reliability-Centered Maintenance. SAEJ 1011 and SAEJ 1012, 1990s. The Society of Automotive Engineers, SAE, published SAEJ 1011, Evaluation Criteria for RCM Processes, and SAEJ 1012, A Guide to the RCM Standard, in the 1990s. These standards provided guidelines and best practices for implementing RCM and assessing the effectiveness of RCM processes. Factor leads to RCM evolution. The traditional approach to scheduled maintenance programs was based on the concept that every item on a piece of complex equipment has a right age, at which complete overhaul is necessary to ensure safety and operating reliability. Many types of failures could not be prevented or effectively reduced by such maintenance activities. No matter how intensively they were performed, there was still a question concerning the relationship of preventive maintenance to reliability. In response to this problem, airplane designers began to develop design features that mitigated failure consequences. That is, they learned how to design airplanes that were failure-tolerant. Practices such as the replication of system functions, the use of multiple engines, and the design of damage-tolerant structures greatly weakened the relationship between safety and reliability, although this relationship has not been eliminated altogether. There was still a question concerning the relationship of preventive maintenance to reliability. Experience showing that it was not possible to control the failure rate of certain types of engines by any feasible changes in either the content or frequency of scheduled overhauls. Direct challenge to the traditional concept that length of time between successive overhauls of an item was an important factor in controlling its failure rate. Scheduled overhaul has a little effect on the overall reliability of a complex item unless the item has a dominant failure mode. There are many items for which there is no effective form of scheduled maintenance. RCM benefits. The objective of the techniques outlined in MSGL and MSG2 was to develop a scheduled maintenance program that assured the maximum safety and reliability of which the equipment was capable and also provided them at the lowest cost. As an example of the economic benefits achieved with this approach, under traditional maintenance policies, the initial program for the Douglas DC-8 airplane required scheduled overhaul for 339 items, in contrast to 7 such items in the DC-0 program. One of the items no longer subject to overhaul limits in the later programs was the turbine propulsion engine. Elimination of scheduled overhauls for engines led to major reductions in labor and materials costs, and also reduced the spare engine inventory required to cover shop maintenance by more than 50%. Since engines for larger airplanes then cost more than $1 million each, this was a respectable saving. As another example, under the MSG-1 program for the Boeing 747, United Airlines expended only 66,000 man-hours on major structural inspections before reaching a basic interval of 20,000 hours for the first heavy inspections of this airplane. Under traditional maintenance, it took an expenditure of more than 4 million man-hours to arrive at the same structural inspection interval for the smaller and less complex. Such cost reductions are achieved with no decrease in reliability. On the contrary, a better understanding of the failure process in complex equipment has actually improved reliability by making it possible to direct preventive tasks at specific evidence of potential failures. Reliability-centered maintenance, RCM. Any RCM process shall ensure that all of the following 7 questions are answered satisfactorily and are answered in the sequence shown as follows. In what ways can it fail to fulfill its functions? Functional failures. What causes each functional failure? Failure modes. Understanding failure modes reveals specific reasons, such as fatigue, corrosion, contamination, or human error. What happens when each failure occurs? Failure effects. This outlines the immediate and long-term consequences of failure. In what way does each failure matter? Failure consequences. The impact of failure on safety, production, costs, and compliance is assessed to determine the severity and priority of corrective actions. What should be done to predict or prevent each failure? Proactive tasks and task intervals. What should be done if a suitable proactive task cannot be found? Default actions. If no preventive measures exist, strategies such as redundancy, design modifications, or operational changes must be implemented to manage failure risks effectively. Top management responsibility for asset management. Setting priorities. Identifying and ranking key objectives based on their impact on asset performance, reliability, and overall business goals. Allocating resources. Ensuring financial, technological, and human resources are adequately assigned to meet asset management objectives effectively. Fostering collaboration. Building a work culture centered on teamwork, shared accountability, and continuous improvement to drive asset performance. Aligning objectives. Establishing asset management goals that support and enhance broader organizational objectives, ensuring strategic cohesion. Measuring success. Defining KPIs and benchmarks to evaluate performance, optimize processes, and ensure continuous progress. A well-structured approach to engagement, collaboration, and resource allocation strengthens the foundation for achieving long-term asset management success. Top management and leaders at all levels are responsible for ensuring that appropriate resources are in place to support the asset management system. Define role, responsibilities, and accountability in asset management organizational. Shall ensure its alignment to other management systems within the organization through appropriate organizational design. Asset management policy. The asset management policy is a short statement that sets out the principles by which the organization intends to apply asset management to achieve its organizational objectives. The policy should set out the organization's commitments and expectations for decisions, activities, and behavior concerning asset management. Examples of asset management policy principles may include commitments for guiding principles for asset management activities, e.g., service delivery objectives are to guide asset management practices and decisions. Adherence to applicable laws, legislation, and regulations. The provision of resources to deliver on asset management objectives and the structure or working of the organization to achieve the organizational objectives, e.g., asset planning and management, is to be integrated with corporate and business planning, budgetary, and reporting processes. The decision-making criteria to be used, e.g., asset management decisions, are to be based on evaluations of alternatives that take into account life cycle, benefits, and risks of the asset. Reporting on asset and asset management performance. Long-term objectives, sustainable outcomes, and stakeholder requirements. Continual improvement of the asset management system.